Yeah, so for the numerator, you want to factor it first. So it's not going to be 12 and 2 because that's not a subtraction sign. Okay, so in order to get a 10, you'd have to have a negative 2 and a positive 12, and that's not going to give you a positive 24. So you're going to have an x plus 6 and an x plus 4. All right. Then in your denominator, what multiplies to give you negative 30, that will add to give you positive 1. Yep. Okay, now resist the urge to cancel out those x plus 6's for a second, because the very first thing you need to do is figure out what your domain is. All right, so think domain, denominator. Okay, so again, you're going to approach this as what would cause your denominator to be 0. And whatever those numbers are, we have to exclude them. It's a lot easier to do this in factored form because what would make this set of parentheses turn into a 0 if x were negative 6 and 5? All right, so you're going to say all real numbers, x can't equal negative 6, comma 5. The opposite, yeah. All right, and then I'm going to add a note here. You're going to have errors in your table for both of those numbers. Okay, again, the more you can see how this stuff relates to your calculator, relates to like the graph, which relates to the table, that is it for this unit. Okay.
Yep. Is always all real numbers and then
yep, all real numbers, and then you exclude certain things. So it's going to be everything except for those two numbers. Yep. And then from here, the domain is either going to turn into, so that negative 6 and 5 are either going to be a vertical asymptote on your graph, or it could be a removable discontinuity, or it could be 2 of one and none of the other, or vice versa. But these three are super closely related. So I'm going to do this by hand first, and then I'll show you how it's related in the calculator. So if you go over here, now we can go ahead and cancel out these x plus 6's. What does that create? A hole. Okay, so you're going to have a hole in your graph when x is what value? Can you see that green okay? Okay. So it says hole in your graph when x equals what number? Not 6, negative 6. Okay, so remember the hole is just a single point on your graph, so it's an ordered pair. So I'm going to go over here to removable discontinuity, put a parenthesis, and put negative 6, and I'm going to let it sit there for a second because I'm not going to find the y coordinate until a little later. The next thing we're going to do is figure out what your vertical asymptotes are. Now here's the thing. Since this negative 6 turned into a hole, there is a strong chance that this 5 is going to be your vertical asymptote. But the way you tell it is whatever's left over on the bottom, if you set that equal to 0, you're going to have a vertical asymptote at 5. At this point, I would graph it. Or you could graph it from the beginning. It doesn't matter. But when you graph it, make sure you type in the original problem, not your factored form. Because what if you factored it wrong? All right, if you factored it wrong, you're not going to catch that you made that mistake. And some of you sometimes, like, and you saw this on your test that you just got back, some of you I wrote like wrong pair, which just means like you had the right idea, but you picked the wrong pair of numbers. Like if you had told me 12 and 2 up here, I would have written wrong pair. So it just means you factored it wrong. So make sure you type in the original. Okay. So the original, and then don't forget you want to put a decimal point after either the 24 or the 30. All right, and then graph. How many vertical asymptotes do there appear to be? Just one. So like when you have this business here where it goes opposite directions, they could go the same direction, but in this case they go opposite directions. That's a vertical asymptote. It looks like it's over here in this area, which is probably around 5, if I had to guess. Now, if you look back where we said there was a hole, so back at -6, does it look like anything funny is happening back there? No, and you're not going to see anything funny on your graph. For a hole, it's going to look like a regular graph, like there's nothing off about it. All right, but then if you go into your table, there is that error at -6. And then if I scroll down, there should be an error at 5 as well. So if you look at your graph, if there's an error and your graph looks funny, that's your asymptote. And then back at that other error at -6, oops, on your graph, it doesn't look funny, so that's the hole. Okay, so that kind of confirms those things for you. To do the second part of the removable discontinuity, I'm going to remind you how to do this in your calculator first, and then I'll show you how you can do it by hand too. If you want to use your calculator, which honestly I think is the fastest way, keep in the original. And then in y2, put what's left over. So that x plus 4 and x minus 5. And when you graph it, they should create the exact same graph, so it shouldn't look any different. Like when you hit graph, you shouldn't all of a sudden see 2 different graphs. If you do, then you factored it wrong. But if I hit graph, this is especially nice on the color ones because you can see like the red line tracing over where the blue line is. Then if you go into your table, -6 is where we said the hole was. There's still an error in that first column, so that's that original equation with that x plus 6 still in there. But that 0.18, that's that new equation without the hole. That 0.18 is your y-coordinate there. So I'm going to write that down here. I'm just going to round it to 2 decimal places, that's fine. But if I go back to the graph and I scroll down, those 2 errors shows that that's still a vertical asymptote. Okay, and the graph should support that. I'm going to remind you how to find the coordinate of the hole by hand as well, because I don't think it's that difficult. But I mean, again, you can use whichever method you prefer. But if you want to figure out what that value is by hand, I'm just taking what was left over, so that x plus 4 over the x minus 5. I'm going to take the value where we said the hole was going to occur and plug it in for x. So that would give us -6 plus 4 on top, -6 minus 5 on the bottom. Yeah, so when you look at, like, if you look at my keys on Canvas for this stuff, because I'm going to be on, like, normally, you know how I try to type solutions for you for your homework so you can check it in your packet? Typing solutions for this is a huge pain, so I didn't, and it takes up a ton of space. So, like, for this unit, you're going to have to look at Canvas to check your work. But you'll see I do this on all of these. Okay, but know that you could use your calculator. I'm fine with that. I'm going to guess when I divide 2 and 11, it gives me 0.18. And it does. So take your pick. Doesn't matter. And it looks like it repeats, so I guess I should go back and I'll add the bar over the 1/8 if I really want to be technical about what the answer is there. No. Okay, so these last 2 that are on here. Okay, I want to remind you that both of these you can use your calculator for entirely. Okay, but I want to remind you that you can also use this equation. But let's do the calculator part first. So if I'm going to find the y-intercept, you're going to look at your table. And it's wherever x equals 0. So if I go back in here, go into the table, and even though I still have both of them typed in there, it doesn't matter. Here's where x is 0. If I look over, my y-intercept is -0.8. Easy. So 0, -0.8. The other way you could find the y-intercept without the calculator is, I'm going to do this in blue. If I look at just the numbers that are left without x's, 4 over negative 5. 4 divided by negative 5 is negative 0.8. Okay, so that's a way you could do it without looking at the calculator. All right, and then the last piece of this, the x-intercept, that comes from what's left over on top. If I take x plus 4 and you set it equal to 0, what do you get? Negative 4. So negative 4 is 0 is going to be our x-intercept. But don't forget, you have this graph. In Algebra 2, you found zeros or x-intercepts using your calculator all the time. You could also do that here. If you hit second, trace, and option 2, then it's going to ask you left bound and right bound. So know that this is also an option. I like the equation better just because for me that's faster, but I have a lot more practice with this than you do. But now you could also find it this way. The table will work only if this is a whole number. I realize I still have yellow puffy paint on my nails from that turkey. It was cute. Okay. All right. So that's that whole thing. Okay. The last question on here is basically what we just did, but with like in more of a general way. Okay, so I'm trying to figure out where you're going to have vertical asymptotes, where you're going to have a root or a 0, which in other words is an x-intercept, and where you're going to have a hole. Because I took out the numbers in here, I kind of took your ability to graph this away. So, but here's the thing. And I think you see this a lot in the ACT and stuff. So, like when you take practice tests for the ACT or you take the ACT, a lot of times they'll give you these questions that have a whole bunch of letters in them. And it's crazy overwhelming. What do variables represent in the end? Numbers. Could you, if you wanted to, plug in like 2 for A? Now, when you go to plug in a number for B, I would pick a different number than you chose for the first one. So you could plug in like a 3 here, and maybe something else here, like a 1 or something. And then you could graph it if you wanted to. Okay, so don't forget that like when you see this stuff that's like general and it puts like A's, B's, and C's and all sorts of other letters, like they're still numbers. And if you're better visually with like numbers and trying to figure it out that way, then I would use it that way. All right, but if we look here, what's going to happen with these x plus A's? They're going to cancel. So what are those creating? A vertical asymptote, a root, or removable discontinuity? If they cancel, we removed it. So it creates a hole or the removable discontinuity. So that's what that is. But what's going to be, it says for what value of x? So if this were x plus 2, for example, where would the hole be at for the x value? 2? Negative 2. So if this is an A, it's a negative A. All right, so now if we look at what's left over, we have something on the bottom.
Oh, that's what I'm wondering about that giant cafe.
Okay, so with what's in the denominator, this 3x plus c, is that going to be a vertical asymptote or is that going to be a root? It's going to be a vertical asymptote. I know. Oh, yeah. All right, so now in the past we've just had like x plus c, and we said, oh, it's just negative c. But that 3 in front makes things a little bit different. Remember, when we take the opposite, we're always just essentially in our head like setting it equal to 0 and solving. So if I want to get x by itself, what do I have to move first? Minus the c. And then what would you do with the 3? Divide. So you'd have an asymptote at negative c over 3, whatever that one is. But we don't know, so we're just going to leave it like that. Okay, and then the last part of this The only thing that we haven't utilized yet is this. I could have put in here what would be your y-intercept. And your y-intercept would have been negative b over c. Alright. So, if I take this and do the same thing, set it equal to 0, and solve for x. Now, this question I put on your midterm. I did. But it's multiple choice. But I don't know if that makes it easier or...
It makes it harder.
I think it does. But that would be your root or your 0.